Yes, but that is not P. It's rho
Sorry.
for density. That one is rho, not P.
Rho.
Yes, yes,
Yeah,
a
yeah,
symbol
yeah.
for density.
Yeah,
Okay,
that
so,
one.
sorry guys, I'm trying to delete this, but I don't know what's happening. All I'm saying about the I'll be forced to just explain because I'm trying to delete, but actually it signed out when I was trying to delete. So hopefully, so I'm saying in terms of dimension analysis, L is L, mass is M. So if, for example, you're talking about density, or okay, density would be mass over volume. So mass is M, but volume is length times width times height. All those things are measured in length, so that would be length cubed. So a density would be M over L. So M per L cubed. This is what you're seeing here. What you're seeing on the dimension column. I'm trying to delete, but I don't know whether it's internet or something. So we move on. You will read in the notes. It's not very difficult to understand. And so for uh, the the phase relationship, like I said, soil has three-phase system: the solid, which are soil particles, liquid, mostly water, dissolved salts in some cases, and gases, which is air. Okay, now the writing material is working. Then the phase system may be expressed in SI units, either in terms of mass volume or weight volume relationships. The interrelationships of the different phases are important since they help define the condition or the physical makeup of the soil. So these relationships helps in determining other useful parameters, what I was trying to say before, which may otherwise be impossible or very difficult to measure in the field or in the laboratory. So we use easily measurable properties like water content and other things like maybe the void ratio. Uh, Something like porosity may not be easy to measure, but at least we can measure. And then because we are able to measure these, we can express other parameters that might be very difficult to measure, like porosity, in terms of what we know. For example, water content or voids ratio, and so on and so forth. So phase relationships are derived from the basic simple first principle understanding of the geometry and behavior of gases, solids, and liquids. And we are lucky that the liquid we're talking about here is water, so should be fairly simple. So if we use this, soils are generally composed of three distinct phases. These are solids, water, and air. The space occupied by water, uh, the space occupied by water and air is defined at the voids of the soil. The void may be partially or wholly filled by water or air. Completely dry, that means there is no water, so that means the voids are completely filled with air. Or if completely filled with the water, then we have we can say the soil is saturated. So the components may be illustrated as shown in the figure. So here we are saying this is gas. Please make sure you can see gas, you can see water and solid. So either can be partially fully saturated, that means the void. So this is what we are calling the void. This is the volume of void. You'll notice that that's just called E. But I think these are head. Anyway, we are saying the space filled by gas and water is called the volume of voids. Also, if it's saturated, that means that part is full of water. Or if it is dry, that means the voids are filled with air alone. So we need to pay attention to the Vt is the total volume, and Vs is the volume of solids only. Vv is the volume of the void. Volume of water is Vw. Va is the volume of air. So mt over Ws, or Ws is total mass or weight. So when you're talking about the mass, you use m. When you're talking about the weight, you use W. Yeah, so mass is measured in kilograms, but weight is measured in newtons or kilonewtons. So please pay attention. And we are saying here now that the mass of air is assumed to be 0, because in relation to the other, something like water or solids, the air is relatively weightless. So it's a reasonable assumption to make that the mass of water, the mass of air is assumed to be 0. So from here, when we talk about the total volume, the total mass, would be simply the mass of water plus mass of this solid, ignoring the mass of air, because relatively the mass of air is low. This is important. If someone has a question, you can raise. No questions, so silence means hopefully everything is clear. Okay, so we move on. So things start here. So volume of water, the volume of solid is 1 in the specific volume. So that should be uh, a key. So so we start with what is called the moisture content. Moisture content is the moisture of the weight or mass of water over the mass of solids. All right, and okay, this is your first course. So I'll try to understand. I'll try to explain. So, for example, when you have a tin here, you put the solid, the so you first have to weigh the mass of wet soil. I'd say wet soil. That means mass of wet soil plus the container. So maybe say that is so plus the container, so say that is 50 grams. Then you have to weigh mass of dry soil. So dry soil plus the same container, so say that is 35. Then you have to weigh the mass of the container alone. Say it's 10 grams. Okay, so dry soil, that means you have to put in the oven. You put this, so you have to say this is wet soil plus the container. You put in the oven for 12 hours, and you have to keep the oven temperature between 100 and 105 degrees centigrade. Anyone who has an idea why we have to do that? That has some
to completely remove all the moisture.
Yes, because the boiling point of water is around 100, so we get it a little bit higher than 100 just to make sure there is no water. But you should not go beyond 110 because you want to make sure this is soil. Otherwise, you don't want to disintegrate the soil. So at such temperatures, remember we talk about the clay, and clay kind of, some clay is active. So at certain temperatures may try to dissociate now, or try to break down the chemical component. But you want to keep the fact that you are testing what soil. So if a chemical reaction occurs and then it converts to something else, then that's not right, because then that no longer you're talking about the soil. So you keep 100, between 100 and 105, but don't go beyond 110. So from here you can get the mass of wet soil mass uh, mass of wet soil. You can get mass of wet soil would be 50 minus 10, right? 50 minus 10 would be 40 grams. Then mass of dry soil would be 35 minus 10, so 25. Then the mass of water now, mass of water would be these two, the difference between these two, this is 15. And then now the water content, we said, is the mass of water over mass of solids. I hesitate to delete this because it refused. Let me try. So let's mass of would be 15 divided by 25. Okay, yeah, 15 divided by 25. Then you can express that into percentage. So that's what we do. So that's the weight of water. Well, that's, in other words, the water content. Yeah. So normally we just present it like this. Or if you prefer to use the weights, still you should get the same thing. Now the void ratio is very simple actually. The void ratio is the volume of voids over the volume of solids. This is the primary definition. But in all these derivations, we are assuming we are talking about specific volume. So for specific volume, the volume of solids is 1, and therefore we say the E is the same as the voids ratio. Very simple, right? Hello?
Hello to you.
Yes.
You understand, yeah?
Yeah, we
Yes,
are
sir.
sir.
Okay, so let's proceed. I'll try to go slowly. So the porosity we are saying is the volume of voids over the total volume. Okay, the total volume, let me highlight. The total volume is the volume of voids plus the volume of solids. I even try to draw for you here to remind you. These are solids, this is water, and this is air. But we said the volume of voids consists of volume of air and water. It's called the volume of voids, isn't it? Is it? But this
Yes,
is
yes, sir.
this is 1, and this is E from what we already proved, and this is E. So therefore N is actually E over 1 plus E. And the reason I was saying this, this one you can measure in the lab. The voids ratio you can measure in the lab, some effort. But porosity is quite difficult to measure. Well, you can measure for porosity, but it's with some effort. So if you only have if your equipment can only measure voids ratio, then you can avoid the hassle of measuring porosity. Okay. So imagine in the exam you are told to prove that and you cannot prove it. Very simple. So once you express, the key is once you express the primary definition, then from specific volume, equals 1, and then the volume of voids is E. Very simple. It can easily be proven. So now it's a little bit um, no. Okay, things will get a little slightly, but if you reason, you will see that it's quite simple. Then the specific gravity, I think this has this you should know, is the density of solid over density of water, or if you want to talk about the weight, the unit weight of water, of not weight water but solids over the unit weight of water. That gives you the specific gravity, right? Then the degree of saturation uh, uh, is the volume of water in the voids as shown. We will try to derive. Please don't get lost. I think is simple. So stay with me. We said the degree of saturation is volume of water over the volume of voids, right? Because we said the voids has either voids in total have air and water, all right? So if you have water and air, uh, so the degree of saturation is the volume of what voids over, I remind you here, we have the volume of solid, this is 1, and the volume of air, of water, and then we have volume of air. This is what we are calling this, the entire thing is what we are calling volume of void. So if you want to know degree of saturation, is volume of water over the total volume. Okay, that's the degree of saturation. Okay, so now but volume of water is what? Because we have to substitute the volume of water here. What is the volume of water? The volume of water is mass of water divided by the density of water, from basic principles, because we say density is mass over volume. Stay with me. I think this is straightforward. That should also be straightforward. But from what we have done previously, so we said water content is mass of water over mass of solid. So you should not see why mass of water here. So see from here, you cross multiply. But mass of water is that because we intend to substitute this mass of water. Okay. Here we are interested in volume of water because we want to substitute it back there. But note that the mass of solid, because then we are saying the volume of solid is from basic is mass of solid over the volume of the solid. So then it follows that that is true. But we are talking about a specific volume. So therefore, the mass of solid is just the density of the solid. But the density of the solid from here, yeah, we can go back. Here we can go back. But the density of solid from here, the density of the solid from here is specific gravity of the solid times the follows from here. Alright? So that you should not see a difficulty with that. And the intention is to substitute this back here. And so from all the things we have talked about, this should not see why that is not true, why that is true. And And if that is the case, then we can substitute all this thing we can substitute here to get the volume of water. All right, so let's substitute here. So the volume of water would be the mass of water, which is WGS gamma water over gamma water. Yeah, so you can see why this is WGS. All right, so then we are saying that for the degree of saturation, the degree of saturation would be VV, V water, but V water is this, is there, WGS over VV, but VV is E. VV is E. So you should not see a difficulty why that is correct. And like I've said, that would be quite difficult to measure in the laboratory. So, but we can measure water content, the specific gravity you can measure, and you can also measure the porosity. So you will know the degree of saturation very easily. And we are saying that it is worth noting that the resultant equation has a degree of saturation expressed in terms of water content, specific gravity, and void ratio. Water content can easily be measured in the laboratory or estimated in the field using sandbath method. Specific density for most already known, or you can easily measure without introducing. In fact, the specific density is maybe between 2.6 to 2.7. Right, so that's the point. Unless someone has a question, this is just explaining that it's easy to express. Now that we have the degree of saturation, difficult to measure, but the W, the GS, and the E are easy to measure. So if you're asked, for example, why the phase relationships are important, then this is the point actually. And then air content. Are we still together? I hope I did not lose anyone.
We are together, sir.
Yes. So air content is the volume of air over the total volume. But remember that the volume of air, you remember this? This is the volume of solids, sorry, then volume of water, and then volume of air. But this is called the volume of voids. That means volume of air is the volume of voids minus volume of water, but the volume of voids is E from the previous derivation, and then volume of water is WGS. We already know that. And then the total volume is actually from here is volume of voids plus Vs, but volume of voids is E, so, and volume of Vs is 1 for specific volume. So you should not see a difficulty how this transforms to this, how this transforms to that. So air volume is E minus WGS, should be fairly easy. All right. Now we know that from here, actually, we know, we recall this, right? So we use that here. Uh, so if you substitute, SRE, so A equals E minus SRE E, over 1 plus E. I want to see the person who is concentrating. If you factorize this equals A, how do you factorize E over 1 plus E, because E is common, into what? E into 1 minus SR. Good. What is this? What is that?
That is porosity.
Are you sure now? Well, okay, let me check. Yeah, correct. Sorry. Yes, you're correct. That's porosity. Yes. So A. Anyway, this is what we're trying to drive here. See, it's very simple, right? Hello.
Yes, we are following, sir.
Yeah, should be simple. And then you check. Don't think. Don't say. Don't think a little too much. But just think. For dry soil, what does the for dry soil, what is the degree of porosity? I mean, what is the degree of saturation for dry soil?
It's zero.
Is zero. So that means the air content is equal to the porosity is equal to the air content. Basically means that the volume of voids has air everywhere, right? And when soil is completely saturated, the degree of saturation is if water is completely saturated. If the soil is completely saturated, the degree of saturation is hello,
It's one.
is 1. So it means 1 minus 1. So air content is 0. Makes sense, right? Okay. Makes a lot of sense. And despite the simplified assumption, someone asked me why we said this is 1. You can see the results should not defy common sense either way. So makes sense. And you can be sure that this is going to, you will be told to prove any of what we have derived before, but we are not done. So we say the density of solids. This is the ratio of the mass of solids, completely dry soil without water, mass of air inside the soil from its density is relatively small, therefore can be ignored to the volume of solids alone, neither considering the volume of air nor water. The expression for this ratio is shown. Similarly, the unit of water can be obtained. Anyway, we are talking about the density of solids. Those let's go to the maths. I think is more interesting. So the density of this is true. Density is mass over volume. But we have said that this is 1. So therefore, the density is the same as the mass. Uh, so the same thing we are saying here. But when you express them in terms of uh, the the specific unit weight. Now let's see if you can follow this. The same thing. So this is from the previous uh, understanding, and then this is also from previous understanding. And with the two, you can combine because we know mass of solid is a specific times. Anyway, the mass of solid is first of all is volume of solids times the density of solids, right? but the density of solid is this is so here. So okay, so to get the mass is the density. So mass would be density of the solid, density of the solid times the volume of the solid. But the density of the solid, because you remember specific gravity is density of the solid over density of water. So you should not see why. So this is the, that gives you the density of the solid times the volume of the solid. That's the mass of the solid. Now, if the bulk density is mass of water, mass, no, 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 no. So this is we are just trying to. So if, for example, we say mass of water over the volume of solid, so we try to, what does the mass of water involve? The density of water times volume of water over the volume of solid. Uh, so, but now if you divide, because the volume of solid, we can decide to divide to multiply. If we introduce here, sorry, if you introduce Vs over Vs, you are not changing anything. Okay, one, you have not changed the principal. The principal equation is the over Vs. I can decide to multiply by Vs over Vs, because in any case Vs over Vs is 1. But that enables me to express this, to give, to express this equation in that manner. So once that is the case, then we say density is mass over volume, but this is total mass. So mass of water plus mass of solids over volume of water, no, volume of solid plus the volume of void, because that is what the total volume. So this is what we are trying to do here. This is the mass of solid, this is the mass of water, and this is the volume of solids and volume of voids. Nothing prevents us from, so if you want to make it simple, we should, sorry, I think this is wrong. You should divide by the volume of voids, the volume of solids, because the volume of solids is 1. And remember this expression, I think we've done this so many times, that leads here, and with that the mass of water comes to this. All right, so having done that, so the bulk density is simply mass over volume, which is mass of water plus mass of solids over volume of voids plus volume of solids. So this is one way of expressing the mass of water from up there, and this is, I think, is very easy, because we know from the logic that we have proffered here, up here. So when we factor in the density of water, this is what we come up with. And if we express in terms of the water content, this is what we come up with. So this is just the same derivation when we are talking about the uh, the same derivation when you are talking about the now when you express in terms of the weight, in terms of the weight, but the same thing. So any of these you can be told to prove should be straightforward if you think about it. And so this becomes, this is, I think this is an expression we have already proffered, but something interesting I should point out For example, if water is completely dry, if water is not water, sorry, not water. If soil is completely dry, the degree of saturation is for dry soil
Zero.
0. So for dry soil, degree of saturation is 0. So from here you can easily get the dry density. Dry density is WGS over 1 plus E, because this one is 0, right? This one becomes 0. Similarly, you can get the gamma saturated if if the soil is completely saturated with water. Anyone? I need guidance for saturated density. First, for saturated soil completely filled with water, the degree of saturation we already said is 1. So someone please tell me the expression for saturated density. Modify basically from here should be simple. Anyone? Surely. Can I point at random? Class rep. Class rep.
Yes, yes, sir.
Give me the saturated density because should be easy. What is the expression?
Just a minute, sir.
For saturated soil, SR is 1. So just here, substitute here. Should not be difficult. And that is called gamma sat equals. Class rep, are you sure you're in this class?
Yes, sir, I'm there.
He is taking too long. Someone else? Someone else, please. Yeah. Someone else? Mwangi.
Allow me to try, sir.
Yes.
It is density of water over 1 plus E
Yeah, 1 plus C, correct.
into E plus GS.
Yeah, there's nothing to try there. You're even shocking me. It's that simple.
Oh,
Yeah. So the same thing I said, degree of when it is dry is called gamma D. And so this is gamma water over 1 plus E. So when you are told to prove this in the exam and you okay, this would be 0 plus GS. And that's why I said gamma water GS over 1 plus E. Should be straightforward. And actually that makes my work very easy because that's what we are going to next. And because you already proved it, there's no reason to gamma sat. This is what we said, and gamma dry. We already proved that very easily. So, any question? Should be no question. Okay, should be easy. So there is what we call the submerged unit weight. Now this is important. Submerged unit weight is usually called gamma submerged. This is the gamma sat. minus gamma water. Now this is important because when the pore water pressure increases, if you've seen, there's something we call quicksand condition. This is in small scale, but in large scale it's called liquefaction. Quicksand condition is when it rains and you have loose soil, not soil, loose sand. Sometimes immediately after it rains, you can see water gushing out of the soil, carrying itself carrying sand with it in a manner, so it looks like the sand is boiling. That's why we call it. Actually, another name for it is called sand boiling. Those who come from sandy areas is quite common, and especially when you have loose sand. And this is a problem with construction on loose sand. Now, liquefaction is when this happens on large scale due to earthquake. So this is the explanation, or this is the reason that for example, when so gamma submerged is gamma saturated, gamma water. But now when remember, we are saying sigma, the effective stress, is the total stress minus the pore water. Now what happens in quicksand condition is that, so when for example, sorry, no, this is not right. The expression is not right. Effective stress is total stress minus so what happens when two questions for you, or we think together. When water goes down, when the pore water goes down, what happens to sigma prime? Goes up or goes down? I'm waiting for response. Hello?
Yeah, it goes up.
Yeah, good. And then when the pore water pressure goes down, goes up, then then then
It goes down.
It goes down.
it goes down. So basically what we are saying, in quicksand condition, this goes up, such that because the water, the strength of soil is controlled by effective stress, so the effective stress, or basically the strength of the soil, goes down beyond the pressure exerted by pore water. So because of the increase of the pore water, the sand particles, they lose their weight. They become kind of weightless, so they can be thrown away because the pore water pressure has already increased beyond the expected value. So then the soil particles are no longer stable. That's why they are carried all over. That's the reason. In fact, the factor of safety against sand boiling or quicksand condition is usually the submerged unit weight, correct? Which, or the gamma saturated minus gamma water over gamma water. All right. So as long as so simply put, pore water pressure increasing beyond the ability of the soil, the shear strength of the soil to withstand. So the soil particles kind of become weightless and they're thrown all over. This is what earthquake also does, and this happens in sandy areas immediately after rain because rainwater increases the pore water pressure as already elucidated. So the submerged unit weight is expressed this way. I had a video for you, but you can get an idea from the photo already. This is under the ocean. I had a video, but the fan either follow or do it. And if you have a problem, you can let me know. So far we are moving to the next area, unless there's a question. No question. Okay. So we are moving on to the soil index properties. And unless you want a break, if you need a break, we can take a break for 10 minutes.
I have a question, sir.
Yes.
In some regions, let's say where in Turkana region,
Mm-hmm.
during sun season,
Mm,
the soil is so dry such that when you do the test, you can even see the farm soils.
mm-mm,
But after one just single rain,
mm-hmm.
it becomes it's like muddy, like this quicksand effect that you are talking about. Somebody can even sing when walking on it.
Mm.
Now, how can we realize such a thing if you go there and start constructing during sun season?
Sandy, what do you mean sandy? Raining or dry?
Rainy and
Sunny.
sunny
Oh,
season.
of course. This is why you are studying this. Of course, there are measures that you can take to mitigate this. But now, for this, the purpose of this subject is you understand the behavior, and then if there's in another if you advance, then we have ways to mitigate this kind of behavior. But no doubt, this is very problematic, causes settlement and induces a lot of stresses in our structures. And of course, this is why you are learning, so that you know how to deal with them.
Noted, sir.
Yeah, so we can take a break for 10 minutes.
Okay, that's fine, sir.
Yeah, so we resume at okay, let's say resume at 4, huh? For 15 minutes is okay. At 4, we resume at 4.
All right.
Okay. So we talk about the soil index properties. The term consistency refers to the relative ease with which soil mass can be deformed, and is used to describe the degree of firmness of fine-grained soils, for which consistency relates to a large extent to water content. We have the four states of consistency suggested by Atterberg as indicated. So we have the liquid state, excuse me, the liquid state. Now, in the liquid state, the soil kind of behaves like a liquid, can flow, and we have the plastic state. plastic state, we have the semi-solid state and the solid state. Now we need to pay attention to the what is happening. The attendance is many people have dropped out or have yet to rejoin. We continue nonetheless. Now the boundary between the solid and semi-solid state is called the shrinkage limit or the SL. The boundary between the semi-solid state and the plastic state is the plastic limit, and the boundary between the liquid state and the plastic state is the liquid limit. Now, a definition of this, we are going to define them in detail as shown as we go by. So, the shrinkage limit. I mean, this can be all these can be represented in a curve or a graph as shown. Now,
Aje, unaendelea?
the the difference. All these things are just described by the water content. The water content. So, as you would imagine, if you continue to pour water, so these are not real values. These are arbitrary values. So I'd say maybe if this is 5%, this would be maybe 12%, and this probably would be, I don't know, 30 or something, to show that the shrinkage limit, the plastic limit, is when you increase the the water content is increasing. But to note that those are boundaries. We are just trying to find the boundary between some state to another, and because that affects the engineering properties, and that's what we're interested uh, in the field, or at least for engineering purposes. So in the solid state, there will be no change. Please tell those who are joining this class to join, because it was 12, now only 8 or 7, I don't know. In the solid state, there will be no change in volume of soil mass accompanying change in water content. In the remaining three states, in water content is accompanied. In the remaining three states, increase in water content is accompanied by increase in volume of soil mass and decrease of water content by reduction in volume of soil mass. In the liquid state, the soil behaves like a liquid, already said, very less shear strength. In the plastic state, the soil mass can be deformed without cracking. In the semi-solid state, the soil mass cannot be deformed without cracking. So those are just some of the behavioral characteristics that distinguish. So we are saying in a liquid state, the soil more or less is acting like a liquid, so the shear strength is close to zero. And for in a semi-solid state, the mass a soil mass cannot be deformed without cracking, but in plastic state, the soil can be deformed without cracking. But in semi-solid state, it cannot be deformed without cracking. And in the so that covers all the behavior, uh, all the behavior in those states. And so the water contents which arbitrarily define the boundary between the four states of consistency are referred to as the consistency limits or the Atterberg limits. Three consistency limits are liquids limit, LL, the plastic limit, uh, PL, and the shrinkage limit, SL. Liquid limit is denoted by LL or WL and is boundary between plastic and liquid states of consistency. It is the minimum water content at which the soil still flows like a liquid. Yeah, so the liquid limit is just, for example, liquid, the water, beyond that point, the water is bound to behave like a liquid, but this is the minimum water content at which the soil starts to behave like a liquid. Yeah, so for example, if between 40 and 40, if above 40%, the soil is behaving like a liquid. So the minimum, let's for example, water content of 40%, at which the soil starts to behave like a liquid. Now that's what the liquid limit is. Now liquid limit is defined as the water content at which groove cut with a standard grooving tool in soil. Part take in the cap of standard liquid limit device closest for a distance of 13 millimeter or half a inch when the cap is imparted 25 blows. This will get clearer in the next slide. Plastic limit is denoted by PL or WPE and is the boundary between semi-solid excuse me and the plastic states of consistency. It is the minimum water content at which the soil mass can still be deformed without cracking. A plastic limit is defined as the water content at which the soil mass can be controlled into a thread, can be rolled into thread. This is wrong. This thread, please note that thread, not thread of 3 millimeter diameter, and the thread first shows signs of cracking. We'll get clearer in a minute. Shrinkage limit is denoted by SL or WS and is the boundary between the solid and the semi-solid state of consistency. It is defined as the maximum water content at which there is no reduction in the volume of soil mass accompanying reduction in water content. Now, this is an overrider. It is convenient when you, okay, now I have to preempt what we are going to do in the next slide because it's getting increasingly difficult not to. Now, normally to determine the water content, okay, I'll come back to this slide so that you understand. Yes, to determine the water content, we use, I think this is not right, device. Autocorrect is, that's not how to write device, please note. But it's called Casagrande device. So, the Casagrande device, you use this tool here, the grooving tool. Those who cannot see it properly, something like this. Something like, and with some tip here. With some tip. Some tip. Then you use the, you fill this cup, everything is full. Is full. Then you bring the groove, this groove here. Then you swipe here once to make the space that you can see here. To make this space, you swipe once, very fast. So the issue is you take, I mean the procedure is you take your soil as defined by either ASTM or the British standards, STM or ASTM, sorry, or the BS standards or Euro codes, whichever standard you're using. You take some amount of soil, you mix with increasing amounts of water. So once you increase mix, you pour water into the sample, you mix properly, and then put in the cup as shown, and then you cut with the groove. Once you cut with the groove, there is some rotation mechanism. This is the side view. You use this to rotate. You just do a motion. You rotate this way. Of course, when you rotate this thing, this cup here lifts up and drops at the bottom. So every time you rotate, then it goes up and drops. So with the action, that action, then this part, the soil, the soil that is cut or that is apart, can rejoin as shown. So this, when you do that, you expect this soil to be moving like that. So when it rejoins for half an inch, then you stop the experiment. That is recorded at the number of blows n. Okay, so I've explained that. So this can be done manually. There is a tool you can, the Casagrande tool. This is the manual. You can do the action of rotating this manually, or there are machines. There are electrical. So this is the electrical one. You can use electricity, or you can do it manually, whichever way. How? So it depends on the level of sophistication of your equipment. So that is that. So then the reason for this is that at the end of the day, so once you do that, you take this, especially this part, to the oven, like I already showed you, to determine the water content. I think I already elucidated how to find the water content in the lab. So what you will do is you take several values. Several What's happening? It's refusing to draw. Okay, let's see. Yeah, okay, you take several value, and this is normally a log scale. This is normally a log scale. And you draw number of blows. So the number of blows are called n. Sorry, is it just a minute? Yes, this is typical curve. Yeah, the number of blows. So number of blows and then the water content. So like I said, you increase the amounts of water content. So for example, the first water content is 5. The first water content is 5%, and the number of blows is 10. So this is what we are saying: 15, 20, and maybe 25, 30, and so on and so forth. So this is what we are saying here. Make sure that you make the counts read around 40, 30, 20, and 10. The reason for that, because this is a log scale, so it's easy to plot them without introducing errors. So at the end of the day, you will come up with a nice curve, a nice curve. No, 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 that's not right. I've deleted everything. Anyway, 10, 20, this is the log scale, n, water content. Because of course, when the water content is low, you expect a high number of blows. So you get a curve like that, a straight line. Maybe it's difficult to get a perfect straight line, but they will scatter around a straight line, and then you you find the best fit. Now the best fit, we define when the number of blows is 25. That is your liquid limit. So you read the water content, that becomes a liquid limit. So what I wanted to explain is just this, that you make sure that it's difficult to do that because you don't know how much water content, how much water to add to give you those number of blows. But to make it easier on your part, of course, with the experience, you'll be able to tell. But make sure the number of blows are around near 40, 30, 20, and 10 to make it easier to plot on the log scale. This is what we are saying. So I think I already explained this, and then we describe we define the liquid limit as the water content when the number of blows are 25. Now you could also determine the liquid limit using penetrometer, or cone penetrometer. It's called cone penetrometer. The penetrometer is fitted with stainless steel cone having smooth polished surface. The cone is approximately 35 millimeters long and has an angle of 30° plus 1. I think plus, or should be plus or minus. Anyway, The mass of the cone together with its sliding shaft is 80 grams. So this is the assembly. So the mass of the entire thing should be about 80 grams. A metal cup about 55 million in diameter and 40 millimeter deep is used to contain the test. So what we try to do, you have seen the apparatus. The same thing. You mix according to the standards. You mix water with increasing. We mix soil with increasing amounts of water. Then you put in the cup. You put in the cup every time you. Sorry, let me draw a better cup. You put inside the cup to the brim, to the brim. So once you mix, just like Casa Grande, you in the Casa Grande case, you put the cup, you put the water, I mean not the water, sorry, the soil, so that it fills the cup, and then you bring your the tip of your penetrometer, preferably at the center, somewhere there, and just to make sure that is temporarily touching for 5 seconds. As you can tell that depending on the water content, the penetrometer will penetrate the soil so much. Of course, as you can imagine, when the water content is low, then the penetration will be little. So say 5%, and then your only water content is 5. Uh, okay. So if the water content is say 5, then the penetration P, let's say P, I don't know, P, something is, the thing doesn't want me to write at the edge. So P would be say just 2 millimeter, and then if if 10%, maybe P is, I don't know, 6, 15 penetration. These are millimeters, okay. Maybe I don't know, 8 or some value 12, depending on the soil. Again, you're able to get a nice some nice data there, and then you can draw a curve as shown. Actually, yes, and then we define the the liquid limit as the penetration I mean the water content when penetration. So the water content here, and this is the penetration. So when the penetration is 20 millimeter, that gives you the liquid limit already. So not in penetrometer, the liquid limit is determined when the penetration or the cone can penetrate the soil 20 millimeters, and in the Casa Grande, when the number of blows is 25, the water content, when the number of blows that can rejoin the grooved part of the soil set apart can rejoin for half an inch, or about 12.5 to 13 millimeters. And so I don't know, this what I think this is already what I'm explaining, but let's see. So the a sample of 250 grams, I think this is defined in the standard, passing through 425 micron sieve is, excuse me, is mixed with distilled water. A soil paste is filled in the metal cup at the surface track of level. The cone is lowered to just touch the surface of soil and then released for a period of 5 seconds. The penetration is recorded. The cone is lifted and cleaned. The test is repeated over 4 different moisture contents. The moisture contents used in the test should be such that the penetrations obtained lie between a range of 15 to 35 millimeters. To obtain this, the liquid limit cone penetration against moisture content, both on normal axis to give best fitting. So the difference, this is plotted on normal axis. The Casa Grande case is a semi-log axis. Semi-log, just to make it easy to interpret. Actually, that's the norm the ordinary way of doing it. But in actuality, you can also plot in ordinary curve. But in ordinary curve would be different, would be difficult to the 10, the 10, 20, 30. So it's better to follow the convention. But also there are I mean, in practice there are standard curves. You don't need to worry about the kind of curve, because they are standard curves, empty curves. You just can obtain one and plot and present your results. So we said to give the best fitting straight line, the moisture content corresponding to cone penetration of 20 is taken as the liquid limit of the soil, which for all practical purposes is the same as LL obtained by Casagrande apparatus. So research has been done, and it looks like when penetration is 20, that coincides with the results from the Casagrande tool. Now there is what you call one point LL test. As engineers, we are always interested, because for example, you have a project in Turkana, or I don't know, somewhere in Western, and you are consulting in Nairobi. When you go to the field, you need the results pretty fast, because when you keep stuff in the field or in the coast, you are paying for hotels and all these things. So you need to do things economically and do them correctly. So sometimes we're interested in getting an idea fast, of course, economically, with not spending too much time or too much money. And of course, the reason for all this is for economic design. All the study we are doing is to make sure we are doing sound things economically. So sometimes we might be interested in one point liquid limit test. Please note that this can only be done of soils with similar geologic origin, and given you already have what is called the flow curve. Maybe I did not explain. The flow curve is the one, when this the log scale, and number of n and water content. This is what is called the flow curve. So when you already have the flow curve and the gradient is better, so and probably that means you have done work with that kind of soil before. So for soils of similar geologic origin, the slopes of the flow curve are similar. Then all you have to do is obtain water content, the natural water content, because when you obtain the sample, it has some default water content, then what is called the natural water content of the sample, with closure of the groove at any blow, uh, and use the following relationship. So as like you when you have access to the Casagrande tool, then you already know the gradient of the flow curve. All you need to do is fill in this the tool. I'll draw a terrible one, but just to make sure you can understand, this is the tool, the groove. I'm trying to draw the cup, the Casagrande cup. So something like this, and then you put your, let me use blue. You put your soil here, soil there, and you fill it. So this is the natural soil. You don't add anything, and then once you put a groove. Once you do the groove, and then this becomes your the separation, and then you roll, rotate this, you rotate, uh, you rotate. Once you rotate, and then you find the number of blows, and the natural water content, maybe n is 10, I don't know, depending on the kind of soil. Then you just, that's all you need to know, and then the water content and the number of n, then you can know the liquid limit very fast. But please note that you must know the gradient of the flow curve, and this has to be soil of the same geologic origin as the one whose flow curve is already known. And for the best results, blow count n should be between 10 and 40 as stated earlier. So the plastic limit is determined. The sample of soil is mixed with distilled water until it is sufficiently plastic to be rolled until a ball between palms of hands, uh, uh, into a ball between palms of the hands. A small portion of the ball is then rolled into smooth plate into thread of 3 millimeters diameter, and the thread is looked for signs of cracking. If no cracks are seen, the thread is picked up and again rolled into a ball between palms. The water content is reduced by heat of the fingers. The ball is then rolled on smooth plate into thread of 3 millimeter diameter as shown. The steps are repeated until 3 meter a thread. I don't know why this thing keeps saying thread. Thread, not thread. Thread first shows signs of cracking. It's gonna get clearer here. Yes, this is what you try to do. You try to play like in kindergarten. So you roll like this, and then the plastic limit will be very clear when it starts to roll like this. If you played in, is it kindergarten? I don't know. Maybe some of you, this class has people who I think who are sufficiently old. So you must have gone to kindergarten. The ones the young kids of today maybe did not experience. I went to the kindergartens in the village. You play with clay until you know this point. You can when you roll.
It
Uh, i-
was art and craft.
yes. You roll, and then this will happen. You will certainly know when it happens. Just to explain a little bit here, these tests are usually done with either the Casa Grande or the con penetratometer, because actually you are interested in this thing we are calling the plastic index. Remember when we are talking about the clay, why it's problematic? The plastic index is the same as the liquid index minus the plastic limit. No, not the liquid. This is the liquid limit already determined from Casa Grande or from the penetration con penetrometer. Now the plastic limit has to be done together with this. Question for you. Maybe if you've done it in the field, I believe all of you, most of you, or all have some experience in the field. So if, for example, you are doing Casa Grande, let's say the water content and the number of blows 5, and say this is 55 blows. 10, say these are 40, and 20, say they are 20 blows. They are supposed to be 4, and say maybe 35%. You only need 10 blows. Question: which of these, because you excuse me, these soils are always because you use the same soil with you keep adding the water content. So which soil can you pick here to roll for the liquid limit? The soil, the first, the second, or the third, or the fourth? One. No. And one, two, three, 4. Which soil will you pick to do the water, the liquid? I mean the plastic limit. Which sample? Yes. Anyone? I've never had a lady. No, no, there was a lady. Yeah, now I need a lady. Catherine or who? There's Catherine. There's Christine. I think Catherine has spoken. Christine.
Yes, sir.
Yeah, which one will you use for plastic limit?
I'm not very sure. I'm not very sure because I can't see them clearly.
The one, two, three, four, or four. We are increasing water content. Just say one or two or three or four. But no, one
Oh,
has, yes, one has less, two has more, three has more, four has the highest water content.
so one.
Okay, no, that's not right. Because one you may not even be able to roll. Anyone else? Catherine, Catherine, you're
Oh, sorry.
okay,
So it's
yeah.
an increase.
Three. Why? That's a very interesting choice. But you either, so I think if one was wrong, then the obvious answer is four. Three, because the reason is you don't actually know what the plastic limit is. All you are sure is that the at when you have passed, because when at four we are saying the number of blows 25. When the number of blows is 25, that means you're already at the liquid limit. At least at the last one, you know we are past the liquid limit because the number of blows is past 20. So at least that one you're sure, but you don't know how. If you are to reduce the water content, you don't exactly know how much will you reduce it to get to the plastic limit. So it's prudent to use the one with the highest water content so that in the process of rolling, you reduce the water content appropriately just to get the plastic limit. Now, if you start with one and you don't know where the plastic limit is and you are reducing, you are lost already. It's two, you are lost because you don't know. But at least with the highest water content, all you know is the plastic limit has to have water content less than what you have. You know that's the highest, but the water content has to be below that. We don't know how much, but the behavior of the soil will tell you. But if you use any intermediate, then you'll be lost for those reasons. So it's prudent. So always helps when alongside when you're doing the Casa Grande or the liquid limit, you use the one with the highest water content to determine the plastic limit. So once you get to this point, you take you put in a container and take to the oven. Excuse me, and then you determine the water content as has been elucidated. Now the test will take some practice. This is just telling you the stories. Looks simple, but will take some practice. But if you played in kindergarten, then it should be easy to identify. Now there's shrinkage limit. This is a little very academic. I'm saying academic because it's a little something you really have to pay attention, but it's very difficult to determine. If you are going to do this in the field, it will take you a very long time, which you may not have, because I can see in my experience with the road. When I was a student, I worked a little bit on roads projects. I usually take samples in the evening or within the day, then you leave them in the oven, then you take results the following day. Now, this shrinkage limit will take you several days from even from the definition. So is that's why I'm saying it's a bit academic. I'll show you. I don't know whether I put in the notes what is used in the field practical and very easy. Yeah, yeah, okay, I did include it. Now, what you do with this is, by definition, shrinkage limit is the maximum water content at which there is no reduction in volume of soil must accompanying reduction in water content. So the first thing you have to note is that even though you continue to reduce the water content, the volume should not reduce. Yeah. So you have to find that maximum water content where there is no cracking. Even though you continue to reduce the water content, the volume of the soil cannot reduce. Very difficult to do, needs attention. So what that means is you will take some soil, maybe saturated or has enough amount of water, and you know the volume and call it V1. Then you have to determine the weight at this stage. Okay. Then, because you do not want to introduce any cracks into the soil or the sample, you have to do air drying. You have to dry under air. What that means is the drying is slowly and controlled, because there is rapid drying that will cause cracks. Because you are concerned with the volume, if cracks are there, they are going to introduce other cavities and then increase or reduce the volume, which is going to give you false reading. So you want to make sure there are no cracks. That is why you have to dry slowly into the air, and that will take days. That's what I'm saying. So if you needed the reading tomorrow, then probably you are not able to do that. Then once you have shown that it can dry, it has dried slowly enough, then you can also can take to the oven. But then you have to identify that transition very fast, because the oven drying is very fast. So you have to know the oven drying, when you change from air drying to oven drying, at point at which, because you see the drying rate in the oven is very high, so you have to identify that transition very keenly, because otherwise when you take it into the oven, the drying rate is gonna increase and there will be cracks, but you don't want that. So once you dry in the air controlled and you are satisfied that probably if you take it to the oven it won't crack, you move. That means you have to try several times, otherwise so if for now you think it's ready, you put in the oven, it cracks, that is already destroyed, you start again. So you have to identify that transition very easily. Now in that process, you will identify a point at which further drying does not reduce, does not contribute, does not cause any further reduction in water content. What has been described there? Yeah. So that in a nutshell, we are saying you are only trying and erring. So this is not, you cannot do this and find the result tomorrow. That's the point. So at stage C of the drying, the soil completely dry, but the volume in is the same as stage B. The weight of the soil is measured at stage C, and its volume is measured by immersing into the dry soil into mercury. So we are putting into the oven to make sure it's completely dry. So even though it's completely dry, the volume should be the same as the volume at some point previously, where there was some amount of water. So if you compare the two volumes, they should be the same, except at stage B there was some water, at stage C there is no water. So but there is no change in volume. That's why we also don't want cracks. So that is your shrinkage limit. Now, and this shows you how to determine the volumes. I think should be that's just some easy mathematics. So shrinkage limit is mass of water in B over mass of solids in C. You use some physics there, you study for yourself. If it is assumed, let's see. So at stage A, fully saturated of soil of V1, and B, mass M1, which on reducing content attains volume 2 and mass M2. If it is assumed that any further reduction in water does not cause decrease in water of the sample, the water content of the shrinkage limit is determined by the mathematics shown, and then I think this yeah, and then I think something is either wrong or these are repeated. Anyway, this slide is repeated, and that's how you find the mass of water in B. And then okay, so that's for this part, and this is why I was saying it's academic, because this is it take you if unless you're familiar, you've done this before, and you kind of have the experience, and it's the same soil. Otherwise, if you're doing it for a fresh for the first time, it will take you some trial and error. So what is done in the field is you use some mold as explained there. You remember me saying the water content. Use the soil with the highest water content when you're doing the Casa Grande or the liquid limit test. Then you apply oil on the mold there, and then you put your mold. You put the water. I mean, you put the soil in the mold. Uh, Once you put the soil in the mold, you put into the oven. This is simple and straightforward. Then you just compare the lengths. All right. So the shrinkage limit is the change in length. So L1 is the new length. The After it shrinks, it will have some length smaller than the original length, and you can see the shrinkage limit is gonna be negative, because the negative value is gonna be a negative value, of course, because the soil after drying is gonna be shorter, obviously, than than it was before. Luckily, we know this is approximate. This is just approximate. Pi should be about twice the shrinkage limit, so you can compare this. Roughly, could be go maybe up to 2.5 or maybe between 1.8. So, but these are some observations, so that when you get strange results, you can check and find out why. So roughly, this is the that is the how to find the shrinkage limit. Now, lastly, we are going to talk about the indices, some indices here, and hopefully, and class rep,
Yes, yes, sir.
do we take a break or I just finished?
I think we just finished.
Okay.
Yes.
So the plastic limit already said is the LL minus PI. Now this gives an indication of how much it will shrink or it will expand. I remember I was talking about Montmorillonite. So for Montmorillonite, this is a very high value, or black cotton soil or soils. Basically, this is a very high value, and because of that, actually, we always recommend, if you have black cotton soil, you just remove it from site, because it causes a lot of problems. If not, if that's the only soil you have and it's on a thick layer, then depending on the structure, we recommend, the only thing you can do is pile foundation. But if you want to do pad foundation, all these shallow foundation, the mat and all these things, we just ask the most of the reports I do to clients, I just say the lucky bit is in Nairobi. The soil, unless you are talking about certain parts of Eastlands or thicker roads, only certain isolated parts. But if you go to Westlands, the city center, the Eastlands, no, Westlands towards Kangemi, there is very thick uh, 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 um, this red coffee soil. Red coffee is not so bad, but still, if you don't design properly, it will cause trouble. But otherwise, the rest of Nairobi, the rock is quite near, and you just find some layers of just a little layer of if it's black cotton, which you just recommend they scrap away, because if you leave it, it's gonna cause a lot of trouble. Again, towards I think Machakos, Kansas City. There's some project there. Okay, anyway, I should not tell you this, but anyway, some around there also has some substantial thickness of black cotton. Maybe about, depends, about six. The highest I've seen maybe to 10 meters. Still, 6 still can be. You can ask them to excavate. But otherwise, if you have a thick layer of 30, or that's a continuous layer of maybe up to 100 meters below, then you have no choice. You have to find another foundation. Another You have to an alternative foundation. Most likely, usually piles. And there's the plastic index. Already we've talked about that. What was this? This is the already we talked about that, so that's no issue. And then we have the flow index. The flow index is you identify two water contents of water contents 1 and water contents 2, and then with the number of the n, and this is how to determine the flow index. So that slope is what the flow index is. Then the liquidity index is the natural water content. Remember what I said, the natural water content as in situ. So you pick the sample, measure the natural water content minus the liquid limit. This is from Casagrande or the penetrometer. Over the IP is the flow index, I believe. No, over actually the plastic index, not the flow index. So over the plastic limit. So that is the plasticity index. Okay, that is, sorry. The liquidity index is the ratio of natural water contact. So this is not right. This is not called plasticity index. This is the liquidity index, sorry. So the formula is okay, but the that name is not right. So that's how to determine the liquidity index. And so this is some figure shows some soil from Ottawa in the US. And then we have liquidity index. Okay, liquidity index is the ratio of natural water content and the remolded states. Yeah, so there are some soils that have there are some soils that the ones that I was telling you are sensitive or active. Under shear loading, actually the soil would be very, it look nice and stable when you are not loading it. But once you load it, it uh, becomes like this, like a liquid. Without adding water, becomes like a liquid. Now, what we suspect is that the loading or the shearing action leads to a chemical, something kin to, it's not well understood yet, but something kin to chemical reaction, that it releases a lot of more water into the sample. So you just, when it is looks stable, this is what you are saying, you measure the water content, and then after disturbing it, and then it's behaving like a liquid, you measure the water content, and then you compare the two. That becomes your liquidity index. Then these are some these are just some explanation as to the behavior the stress strain curves, and so you can read for yourself. And this is also relating with the ideas in fluid mechanics, just to open your view. Otherwise, the most important things we have already covered. So this is just explaining. I told you relating to fluid mechanics, and these are some possible examination questions you're asked to prove this. So up to you. Please make sure you're able to. Just a minute, Catherine. You will have a chance because you are finishing. You make sure you can do this. You can attempt for yourself, and yeah, so you can do that. Yes, Catherine.